Hello everyone, welcome back to Decoder. I am Vihar Sanchit and today we are going to dive into a topic that sounds very complex but is actually very elegant. Today's topic is binary tree array representation. In your journey of life, you have probably seen various tree diagrams drawn for various purposes using circles and lines. But have you ever thought how these tree diagrams exist inside your computer's memory? Well, we are going to peel back that curtain right now and we are going to learn how to map a tree diagram into a 1D array using a few of the formulas that I'll be teaching you within this video. As people in the IT field, when we are going to store data, we have a choice to make. We can use either arrays or we can use pointers. Pointers are like street addresses. When the computer needs to find a child node, it has to look for a certain location in the memory and then jump to that location in order to access that data. So this jumping back and forth can be making the process very slow, and also it will occupy much more memory within the computer. So this is very inefficient when compared to operating with arrays. But arrays are totally different. In an array, the data is stored right next to each other in a neat and straight line. So it is great for the CPU because it can quickly find the correct data that we need, and it is great for us because we can get the results much faster, making it a win-win situation. So this is why for this context we are going to use arrays and not pointers. Over here you can see a tree diagram and its respective array. Now, as you look at this diagram, you may be thinking, the tree diagram doesn't look anything like the array, and how the hell does the tree diagram nodes go inside this array? Well, hold your horses, that's why I am here. Now, I'll teach you how we decide which node goes into which slot inside the array. For this, we are going to use a strategy called level order. Think of it like reading a book. We are going to start from the top and go to the bottom. So if we start at the top, we are at level 0, which is the root node. So that root node is going to be A. So first we take that root node and we place it into the first slot of our array. Then we move on to the next. So now in level 1, we can see B and C. So B is left and C is the right. So we take B first and then we place it into the index 1, and then we take C and we place it into index 2. So now we have index 0, 1 and 2 where sits A, B and C. So now we move on to level 2 where we can see D, E and F. So there D is the leftmost and F is the rightmost. So we are going to take D first and then we are going to place it into index 3. Then we are going to take E and we are going to place it into index 4. And then we are going to take F and we are going to place it into index 5. So like this, using the level order method, we can perfectly preserve a tree diagram inside a 1D array. Now let's talk about the math that we can involve when trying to find out the relationships between the nodes that we have put inside the array. So over here you can see a few formulas that I have shown you. Now if the parent is at index I, to find the left child we can use the formula 2 times I plus 1, and to find the right child we can use the formula 2 times I plus 2, which is the spot next to the left child. But suppose you are at your child node and you want to find the parent node. So then you use the formula I minus 1 divided by 2. And remember, we always take the floor value of these calculations, which means that we are going to exclude any decimals and we are only going to take the whole number value. Now I'm going to mention something important. If you ever face a situation where your array starts at index 1, then you'll just need to change those formulas that I showed you earlier by a little bit and then you're good to go. But nowadays we always use zero indexed arrays because it is important to maintain consistency in our coding environment. By sticking to zero index formulas, you can easily make your code consistent, cleaner, and also less prone to off by one errors that are an absolute nightmare for programmers. Now we'll do a small calculation to see if you are up to speed with what I have discussed up right now. Let's look at node A. It is in index 0. So to find its left child, we are going to use the formula 2 times 0 plus 1, which reveals the index as 1. And as you can see inside the array, B, which is A's left child, is indeed at index 1. We are going to find node B's children. So if node B is at index 1, then node B's left child should be at 2 times 1 plus 1, which is index 3, and that is node D. Node B's right child should be at 2 times 1 plus 2, right next to index 3, which is index 4, and that is node E. So if you look at the array over here, you can see that D and E are exactly in the places that we have calculated. So the math never lies. Now I'm going to show you a mystery spot. If you look at the diagram over here, the node C at index 2 has a left child, which with the formula 2 times 2 plus 1, index 5, and that's node F. But what about its right child? The formula says 2 times 2 plus 2, which is index 6. But in our tree diagram, there is no right child to C or an index 6. In a fixed size array, the index 6 is still reserved for the potential child, and we would usually mark that index 6 as null because this is a very key detail under this topic. And in array representation, it reserves a space for an empty child or potential child which represents the full shape of the tree, even if the branches are missing. Now we are going to go over the pros and cons of using arrays in this context. So is using arrays the best option? Well, not quite. The advantage here is speed and zero extra memory spared for pointers, which is perfect for a complete binary tree. But however, the disadvantage here is that memory might be wasted. Imagine an uneven binary tree that goes only to the right and the left side is kept empty. Now, if you were to record a tree like that inside an array, you would have to record only the right side and leave the left side empty or null, which will require an array of over 1,000 slots. So this is very inefficient for that specific purpose. So the lesson here is that we use arrays for dense or complete tree diagrams, and we use pointers for unbalanced or uneven tree diagrams. This is the end of this video, and I hope you have learned everything that I have taught you about binary tree array representation. So this is goodbye for now. I will see you in the next video.